Continuing on the Bibel lab saga, so last time we left you, we were preparing samples for GCMS, so gas chromatography, mass spectrometry, to figure out what metabolites were in these bacteria. And so previously what we did was we flash filtered the bacteria and we got the bacteria onto these membranes, and then what we did was we dunked them into an extraction solution, which was 60% ethanol and some internal controls, so some molecules that we know will show up on the GCMS, at least they should, and then we know the concentration and we can kind of like compare things to that. So then we stuck those in liquid nitrogen, flash froze them, stuck them in the -80. We took them out, then we did this like vortex dance where you vortex it and then shake it and you vortex it and shake it and vortex and shake it, and that was going to help break the bacteria open. The ethanol then is going to help precipitate the proteins and the membrane gunk. So in order to separate those from the soluble stuff, well then Haley went and centrifuge these, spun out all that crap. Then transfer the supernatant, so the liquid from that, into a fresh tube and added water. And so the reason to add the water was to dilute out the ethanol, because the ethanol is going to make it so that the liquid, when we want to go and stick it in this lyophilizer, so the lyophilizer, a freeze dryer, what it does is it sublimes. It makes you go from a solid to a gas in one step, rather than going through the melting. If we had the ethanol in there, well, if you think you might just put like ethanol, you can put alcohol in like a freezer and it won't freeze. This is because ethanol has a lower melting point than water. And so we need to make it harder to melt if we want to sublime, and so we add water. Adding water raises the melting temperature, which makes it harder to melt, and instead you promote going directly from a solid to a gas, that is subliming. So how does it do it? Normally you go to a liquid, right? Well, it has a low pressure. And so if you think about why molecules are in one state versus another, it's kind of a trade-off between like how much they like each other and how much they like to be free. And so molecules really like to be free, but they hold these bonds to one another, and they hold on to one another. And the stickier they are for one another, so if they're like really polar and stuff, they tend to stick to each other more. And so that makes it harder for them to break apart. But add enough energy and they can break apart. And so that's why if you get hot, you can go from a solid where you really, really stuck together to a liquid where you're sliding around to a gas where you're free. Now, in order to like kind of get free though, you need to either have enough energy in the form of heat, or you need to make it easier to break free in the form of lowering the pressure. So basically the pressure keeps trying to bring the molecules back together, bring them back together, and makes it harder to come apart and harder to become a gas. But what you have here is you have a vacuum. You make it so that you are lowering the pressure. You lower the pressure, you have that vacuum, and now, well, the solid molecules, now all they need is a little bit of heat, they just need like a little push, a little thermal energy, and then what they can do is they can go directly from a solid to a gas. And so what we have in here is we have our tubes and we have our frozen solid liquid. And remember, we have that liquid that has the ethanol and the water. And the water is going to make it so that you don't go from a solid to a liquid to a gas, but instead you go from a solid to a gas. Actually, you'd probably just go from a solid to a liquid and get soup, which is what happened to us the first time we tried because we didn't have the vacuum set up straight. But anyway, hopefully this time will work. And so we add the water, and now if you've seen one of those like phase diagrams where you go like solid, liquid, gas, and there's that point, they all kind of three intersect, that's your triple point. And so we want to be below the triple point, so we have a low enough pressure and we have a low enough temperature when it was frozen, but now we stick it in here, and instead of being in the liquid nitrogen, well, now it's exposed to like room temperature and stuff, and but the low pressure, it makes it so that instead of melting, it goes and sublimes, so that the water is going to sublime out. The water becomes water vapor, and then what happens to that water vapor is it gets sucked out this tube, and in this tube, you can see there's a collector is minus 103 degrees Celsius. Well, what happens is it's really, really, really cold in there, and so the water is gonna get trapped on that. It's gonna get trapped on that really cold thing, and it's gonna freeze. And the water, you get rid of the freezing thing, and so you're not just like reaching some weird equilibrium and stuff. Instead, what's going to happen is that you keep drawing out the water and you sublime all that water, and you should be left with a little powder. And then what we're going to do with that powder is we still need to make it so that the molecules will be volatile so that they'll be able to become gassy when we go and use gas chromatography, liquid chromatography, or gas chromatography, mass spectrometry. So the gas chromatography, it separates these molecules in their gas stage. Now, if we have really polar molecules like the metabolites we want to study, like oxaloacetate, malate, all these good things, they've got a lot of oxygens and nitrogens. They've got carboxylic acids. They've got all these groups that make them really sticky to one another and make it so that they don't want to become gases. And so by adding more organic groups, by adding like methyls and things like this, we basically hide those parts that like to stick together. This makes it easier to come apart. They then fly out into the gas phase, and then they have a column that kind of like separates them. Doing the derivatization, so adding those like other groups to protect the parts that are sticky, it also makes it so they don't stick to the column and weird stuff like that. But then you want it, so that separates them, but now you need to tell what they are, and so that's where the mass spectrometry is going to come into play, and it's going to separate them by their mass charge ratios, and then that will allow us to get like a sort of like fingerprint thing that we can then compare to a database and hopefully be able to tell what molecules are in there. And so this is like our trial run. We're doing things, and so hopefully it all works out. But Haley and Nicholas have been great sports, and hopefully we're having fun. You having fun?
Lots of fun.
Yeah, we're having fun. Okay, Bibel Lab out. So this is what we did last week. We took bacteria and we halted their metabolism by chilling them in liquid nitrogen and then pouring them through a flash filter funnel thing. We trapped them on the membrane. We rinsed that membrane to get rid of the media, the food they were growing in. We had it set up to a trap so we didn't get in the line. We took the bacteria that were on the filter and we pushed them into some extraction solution. So that's our 60% ethanol with our standards. We then shook and vortex and all this stuff, the cells. We spun them down to remove the insoluble things, then transferred the supernatant containing our metabolites into a new tube, leaving behind the filter and the precipitated protein and stuff. We then took that intracellular goodiness and we added water to raise the melting point so that we could promote sublimation, going from a solid to a gas. But right now we have a liquid, so we need to make it a solid. So liquid nitrogen to the rescue yet again. This is then going to freeze it. So we have a solid, we want it to get to a gas. We need to let the gas escape. So we put holes in the lids of our tubes, and now it's off to the machine. So we're gonna change the caps out for the ones with holes in them. Working quickly. We've got about 25 mils into the canister. The lid goes on, hopefully. Little pressure. So we're going to change the caps out for the ones with holes in them. Working quickly. We've got about 25 mils into the canister. The lid goes on, hopefully. Little pressure. Not going to have very much pressure very soon, because now what we're going to do is we are going to put it on this metal rod, turn the vacuum on. We're introducing it to the vacuum. Now we should see that the vacuum goes up because the seal is broken because we introduced the vacuum here. But now this should go down. We should see that so we have a vacuum sealed here, and now the water should be subliming out of our samples and leaving behind a nice little powder that we can then treat and play with. And you can see that the vacuum is already back to going back down, and so hopefully all will go well over the weekend and we won't come back and find soup. Sublime, baby, sublime. So it feels like it's getting cold, but the tubes were cold too. But the heat is getting sucked out from like the out and then being used to do that phase transition where you're going from a solid to a gas. So this canister is getting cold. Hopefully the sublimation will work and we'll just be left with a solid, not a liquid. Fingers crossed.